We are star stuff, harvesting starlight. Our lives, our past and our future, are tied to the sun, the moon, and the stars.
These are the words of legendary US astronomer Carl Sagan. To understand why he calls us star stuff, we can start by looking at the different types of stars that we see in the night sky. If we map stars on a graph with axis of luminosity compared to the sun and temperature, the result is this graph, which is known as the Hertzsprung-Russell diagram. It is not a coincidence that patterns emerge. It is the result of regular stellar life cycles which produce this graph. All stars spend the majority of their life on the main sequence, burning their resources of hydrogen. Stars on the main sequence, such as our star, the Sun, typically are orange-red and occasionally blue. On the main sequence, stars are kept alive by the process of fusion going on inside their core. Fusion is the process of building up smaller elements to make larger ones. In main sequence stars, fusion goes like this. First, two hydrogen atoms, each of one proton, fuse, with one of them becoming a neutron. This produces a neutrino and a positron. The hydrogen isotope formed, called deuterium, then fuses with another hydrogen atom, a proton. This emits a gamma ray and produces a helium isotope, with two protons and one neutron. Two of these helium-3 nuclei then fuse. This in turn produces a helium-4 nucleus of two protons and two neutrons, as well as two hydrogen atoms. This is how hydrogen fuses to become helium. Stars on the main sequence are stable because they have a ready supply of hydrogen, and the outward fusion radiation pressure balances the gravity trying to pull it in. Fusion can only occur in the cores of main sequence stars, where the temperature is sufficiently high that the hydrogen particles are moving fast enough to overcome the electromagnetic repulsion, so that the strong nuclear force can bind them together. But when they run out of hydrogen, they can follow one of two different paths, depending on their mass. If the star's mass is similar to, or smaller than, that of the Sun, then it will become a red giant. Conversely, if it is much larger than that of the Sun, then it will become a supergiant, first a blue supergiant, and then a red supergiant. These supergiants are often over 1,000 million kilometres in diameter. Our Sun is predicted to become a red giant in about 5 billion years' time. During the giant or supergiant phases, the star begins to burn its second fuel source, the helium produced in fusion from the original hydrogen. A star begins to expand when the hydrogen begins to run out, because it starts fusion in the outer layers of the star, when the core is too depleted of hydrogen. Since the outside layers of the star start to burn hydrogen, there is no gravitational pressure acting towards the centre, and so the star expands due to radiation pressure. The surface of the star cools and the temperature drops, which means that the colour of the star moves towards the longer wavelengths of the visible spectrum, red and orange. The helium fusion inside supergiant and giant stars mean that larger elements begin to be formed. First, carbon and oxygen are formed, elements vital for life. In the case of red giants, once their helium stores have been depleted, they collapse even further and form a white dwarf. In white dwarfs and red supergiants, even larger elements can start to be formed by fusion. Carbon fuses together to form magnesium, neon, sodium and aluminium. Iron is the largest element that is formed in a burning star. For stars of similar masses to the Sun's, which became red giants and then white dwarfs, this is the end of their life. They will eventually fade and become a black dwarf, and eventually stop burning at all. In order to find the remaining 64 naturally occurring elements, we have to look back to the red supergiants. These are so large, with so much gravitational potential, that when they eventually collapse when they've run out of fuel and only have an iron core, they collapse under their own weight and explode. This is known as a supernova explosion. These supernovae explosions are the only place in the universe hot enough to form the remaining naturally occurring elements, up to and including uranium, element number 92. These supernovae explosions are so immense that we could easily see it during the day through our own atmosphere if it were to occur at the other side of the galaxy. The remainder of a supernova explosion can be one of two things. It could be a neutron star, one of the smallest, yet most dense forms of stars in the universe. A single teaspoon of these would weigh more than Mount Everest. Alternatively, it could form a black hole. These are the most mysterious and unknown quantities of which we are aware of existing in the universe, where even light is not fast enough to escape the clutch of gravity. For many decades it was believed that only hydrogen and helium were actually involved in the fusion inside stars, since, by looking at the light emitted by stars and using a method known as light spectroscopy, we are able to understand that actually many more elements are involved. These black lines are known as absorption lines. Each chemical element has characteristic light absorption lines, and so we are able to identify which elements are present in the stars. These elements, including zinc, copper and gold, which are formed in supernovae, are scattered across the universe during the explosions. In fact, every piece of gold that exists on Earth was once part of a supernova explosion. This then is what Sagan meant when he said that we are star stuff. We, and everyone around us, and all life around us on Earth, and as far as we know, comprises of those heavier elements once formed in stars and supernova explosions. It is easy then to understand why humanity might want to harness fusion in order to make heavier elements which we might find useful. However, the main reason for trying to harness fusion in the 21st century and the 20th century before it was so that we could harness the immense amount of energy produced by it, an almost limitless source of power. The recreation of fusion in nuclear reactors on Earth has not yet been achieved due to the difficulties of reaching the conditions required. For fusion to occur, incredibly high pressures and temperatures have to be reached in order to overcome the electromagnetic repulsion of protons and to allow a chain reaction of fusion. This chain reaction and the energy it produces would be the only way of harnessing its power. Whilst we have never sustained chain reactions, in specialised pieces of equipment called tokamaks, isolated fusion events have been observed. The specs in this video footage show neutrons produced by fusion in a tokamak. This is the best hope for fusion we currently have.